The application of the Euclidean postulate to find the sum of angles in a figure doesn't just stop at triangles. Once we know that triangles have 180 degrees, which we do now, we can use that to find the total angle measure of a polygon of any size, and that's what this video is about. So first, before we get to actually finding that, we have to talk about what is a polygon. Well, a polygon is a type of two-dimensional figure that is closed, made of line segments, and none of its segments intersect except at the endpoints. So to take a look at what that means, a figure that is closed does not have any breaks in its perimeter, and its segments all intersect somewhere. So this triangle over on the left, there are no breaks in the segments there. The same with the star, the diamond, the hexagon, as well as the arrow. It is made of line segments. And specifically what this is talking about is it doesn't have any curved parts. We can create two-dimensional, three-dimensional figures made out of curved edges, but in order to be considered a polygon, it has to be made of line segments, and none of its segments intersect except at the endpoints. And what that means is we don't have any crossed segments, so that we don't have something that ends up looking like an hourglass. So to see what all of those mean in a different context, here are some examples of figures that are not polygons, though they fit some of the criteria. For example, a polygon being closed, this figure here has a break in its upper edge. It would be a quadrilateral if those segments intersected, but they don't, so it's not a polygon because it fails the closed test. For the two below that, you can see an oval and a semicircle. Both of them very legitimate two-dimensional figures, but they are not made of line segments. They have curved edges, therefore they cannot be considered polygons. And for the bottom one, as we said before, because the segments forming an X in the middle cross and don't intersect only at endpoints, this is not considered a polygon either. It can be broken into two polygons if we split it into those two different triangles, but anything that has crossed edges like that can't be considered a polygon because it fails the idea that none of its segments intersect except at endpoints. So go ahead, pause the video, copy down all of the criteria for being a polygon, come back when you're ready to move on. Now, two of the types of polygons that you may be familiar with as far as their names are concerned are a triangle that classifies as having 3 sides, and a quadrilateral that is classified as a quadrilateral by having 4 sides. Again, tri meaning 3, quad meaning 4. But, of course, we can continue going with naming polygons according to the number of sides that they have. After triangle and quadrilateral, though, we fall into a naming convention where every official polygon name ends with the 3 letters GON, representing a polygon. For example, a 5-sided figure is considered a pentagon, and we can continue up through 6, 7, 8, 9, 10, and then as far as other types of polygons that we might see that have names that are often known, a 20-sided figure is called a dodecagon, and a 12-sided figure rather is called a dodecagon, and a 20-sided figure is called an icosagon. So what I'm going to ask you to do now is pause the video, copy down any of these polygon classifications that you're not already familiar with. So if you already know that triangles, quadrilaterals, pentagons, hexagons, and octagons are what they are, but you need to copy down heptagon, nonagon, decagon, dodecagon, and icosagon, that's what you're going to do. So again, pause the video, copy down any classifications you are unfamiliar with, and come back when you're ready to look at some more definitions around polygons. So in the previous video about classifying triangles, we looked at a special type of triangle where all the sides were the same, and that was an equilateral triangle. As it also happens for triangles, it's one where all of the angles are the same. So an equilateral triangle has 3 sides that are all congruent and 3 angles that are the same, much like this triangle here. You can see 3 angles that are the same, 3 sides that are congruent. Well, of course, that doesn't only happen in triangles, and it can happen in a lot of different polygons too. So for some of these shapes, they have special versions of each of the types of polygons where all angle measures are equal and all side lengths are equal. If every side is congruent to every other side and every angle is congruent to every other angle, that is something we call a regular polygon. So you can see examples of regular triangles, quadrilaterals, which we call a square, pentagon, hexagon, heptagon, and octagon. So go ahead, pause the video, copy down this definition of irregular polygons, come back for the last exploration and investigation with polygons, and then to do some practice problems to end the video. So now that we know about the different types of polygons, we can start to talk about how many total degrees of angles there are within each polygon. Now, as it happens, regardless of the precise shape of the different types of polygons, every quadrilateral has the same number of total internal measure of angles. Every pentagon has the same sum of total internal measure of angles. Every hexagon, etc., all the way through. And to see how many degrees each of those types of polygons have for their internal angles, we can jump back to the idea that triangle angles add up to 180 degrees, and we can do that by using something that's called a diagonal. A diagonal is a line that's drawn in a shape that goes from one vertex to a vertex that is not already connected to. So in the square in the middle of the screen, we can connect the lower left vertex of that square up to the upper right vertex of the square. We can also draw one from the upper left vertex to the lower right vertex, and those are the diagonals of the square. Let's get rid of that for a second. We can also do that with the pentagon, and we'll find that all of the diagonals of the pentagon, when you add them together, create a star shape, because each of those vertices can be connected to two other vertices as diagonals. And the same thing is true with a hexagon. But in particular, we're going to use the diagonals to create some triangles out of these shapes. So in the square, we can draw one diagonal that cuts it into two triangles on the upper left and on the lower right. With the pentagon, if we added one diagonal from the top vertex here, we could see that the left side of that pentagon is now in the shape of a triangle. The right side is now in the shape of a quadrilateral. But if we add another diagonal coming from that one vertex, now we have three triangles. And importantly, all of those angles of those triangles are a part of the angles of the pentagon itself. If we added another diagonal here, suddenly we would have a bunch of intersections that add degrees to the total measure of all the triangles in that polygon that don't exist on the angles of the actual pentagon itself. So we don't want to do that when we're creating these diagonals. Finally, for the hexagon, we can do the same thing. And so what we can see when we do this is a little bit of a pattern emerging. And so if you want to pause the video and see if your pattern is correct by drawing a few more, you're welcome to do that. If you want to pause the video to see a little bit more of this pattern and see if you can put words to it on your own, you're welcome to do that, or you're welcome to stay on the video and listen to the description here. But we start to notice a pattern that in a square, we can create two triangles by adding one diagonal over between its vertices that don't intersect. In a pentagon with 5 sides, we can create 3 triangles. In a hexagon with 6 sides, we can create 4 triangles. And this pattern will continue, and we can see that the pattern will continue because when we add one diagonal that just connects a vertex to 1, 2 over, let's use the hexagon as this example, we actually create a triangle and then a pentagon that has 1 fewer sides than the hexagon it's being created from. So if the pentagon then created 3 triangles, a hexagon will then create just 1 more, because a single diagonal can cut a hexagon into a triangle and a pentagon. And this goes on and on and on, and the number of triangles that can be created is actually 2 less than the number of sides. 4 sides, 2 triangles. 5 sides, 3 triangles. 6 sides, 4 triangles. And each of those triangles has angles that add up to 180 degrees. So for any regular polygon, we can, or any other polygon for that matter, we can split that shape into 2 fewer triangles than the number of sides, and each of those triangles has 180 degrees. So this brings up something that we call the sum of interior angles theorem, or the sum of interior angles formula, for any regular polygon, or for any polygon generally. The sum of the measures of the angles in the polygon with n sides, which we call an n-gon, is n minus 2 times 180. So if it's a 7-sided polygon, a heptagon, it has 7 minus 2, or 5 times 180 total degrees. If it's an icosagon that has 20 sides, it has 20 minus 2, or 18 times 180 total degrees. So go ahead, pause the video, copy these definitions down, and then we're going to go to some practice problems where you practice just using the sum of interior angles formula. So as promised is the last slide of the video here. What you're going to do is pause the video, calculate the sum of the angle measures in a nonagon, in a 15-gon, in an icosagon, and in a 102-gon. Once you're done with those, go ahead and unpause the video. We'll go through the answers, and then we will wrap up. So for a nonagon with 9 sides, the formula again is n minus 2 times 180. So 9 minus 2 is 7. And 7 times 180 gives us a total angle measure of 1,260 degrees. That may seem like a lot of degrees, but remember a nonagon has 9 sides, and each of those angles can be pretty big as far as that's concerned, and also we can split it into 7 triangles. For the 15gon over on the right side here, the 15gon has 15 sides, so 15 minus 2 times 180, or 13 times 180, which gives us a total angle measure of 2,340 degrees. For the icosagon, we have 20 minus 2 times 180, which gives us 18 times 180. And multiplying 18 by 180 gives us a total angle measure of 3,240 degrees. Finally, for the 102gon, that is 102 minus 2 times 180, or 100 times 180, which is, of course, 18,000 degrees. So as a quick wrap-up, polygons are closed. They are made of line segments, and they do not have any intersections of segments that aren't at vertices. We name polygons according to their number of sides, many with names unto themselves, but when in doubt, if we have a 37-sided gon, we just call it a 37gon. And the total sum of the angle measures in any polygon, regular or not, is just n minus 2 times 180, where n is the number of sides.